Hello dear learners, in our today's class we will now move on to our next important part and we will discuss about one of the very important law, that is Kohlrausch Law. So Kohlrausch Law of independent migration of ions. It is a very simple law. What it tries to say is that in the case when we have the infinite dilution, now when the dilution is infinite, we know that in that point of time, be it for the strong electrolytes and be it for the weak electrolytes, they will reach their lambda m infinity. That is also referred to as limiting molar conductivity. So when the dilution is infinite, all the ions inside the solution, whether they are the cations or whether they are the anions, they will have enough space around them. And when there is enough empty space around them, they will not be influenced by any other ion. Suppose this B minus will not be influenced by A plus and this A plus will not be influenced by B minus because there is now enough space around them, and it is all because of the infinite dilution. So when there is infinite dilution, these ions become independent of each other and then they will work independently of each other, or they will work independent of its co-ion, and then they will contribute to their maximum whatever they can to the total limiting molar conductivity of the solution. So see, in the influence of this ion, it was showing some molar conductivity and that was lambda m. But now the influence has been removed because the dilution is infinite. So in that condition, it will show its limiting molar conductivity. It will also show its limiting molar conductivity. So suppose if the solution was A, B and it has been dissociated into A plus and B minus and the dilution is infinite, so the limiting molar conductivity of the total solution AB will be equal to limiting molar conductivity contributed by A plus ion plus the limiting molar conductivity contributed by the B minus ion. It is simply the algebraic sum. That is what Kohlrausch law talks about, and it is applicable basically in the strong electrolytes and the weak electrolytes also, because here the ions have become independent of each other and now they will migrate independently of each other. So for this we can also give a generalized term here. Suppose there is a salt AX BY, so we know that it will dissociate in a form that it will form X A plus and Y B minus. So this X A plus and Y B minus, this will be the stoichiometric coefficients X and Y. These will be multiplied in their limiting molar conductivities also. So when we need to find the limiting molar conductivity of this AXBY salt, so it will be equal to the limiting molar conductivity. Oh, wait. Yes, it will be equal to the limiting molar conductivity of this A plus ion but multiplied by the stoichiometric coefficient, plus the limiting molar conductivity of the B minus ion but multiplied by the stoichiometric coefficient. So this is your final equation which is derived and which is given and put forward by Kohlrausch. Moving on forward, now we have to talk about that what are the applications of the Kohlrausch law. So what is basically Kohlrausch law trying to explain? It is trying to explain you and give you the idea of limiting molar conductivity. Means basically you can calculate limiting molar conductivity with the help of Kohlrausch law. So once you have calculated that, you can also calculate alpha, because alpha was what? It was lambda m upon lambda naught m, and this can only be determined by Kohlrausch law. So you can determine this also very easily. So one of the applications is to determine the dissociation constant. The another one is to also calculate the dissociation constant for the weak electrolytes. Sorry, not the dissociation, this is degree of dissociation. And the second is to calculate the dissociation constant. This is another application of Kohlrausch law. Dissociation constant represented by K, This K is equals to lambda m at a particular concentration, its square, multiplied by concentration upon limiting molar conductivity in brackets limiting molar conductivity minus the molar conductivity. So this is how you can calculate the dissociation constant, but this is applicable to the weak electrolytes only. So what is it? It is dissociation constant K is equals to lambda m square multiplied by C. Lambda m is here the molar conductivity at a particular concentration multiplied by the concentration of that electrolyte divided by the molar conductivity at the infinite dilution, that is what we call as limiting molar conductivity, multiplied by lambda m infinite minus lambda m. So this is one of the another applications of the Kohlrausch law. Okay, now this topic of Kohlrausch law is over. Now we have to talk about another important effect, and that effect is known as Grothus effect. Now in the comparison of another ions, all the other cations and all the other anions, the H plus and OH minus ions, they show a very high conductance. Their conductance and the capability to conduct electricity is very high. Why is it so? And why not the other ions? See, a simple answer can be because H plus being lighter in weight, it can easily move on from one place to another and hence conduct electricity. But Grothus has told something different. He told about the proton jumping mechanism through which the H plus will conduct the electricity. The proton jumping mechanism says that suppose here we have this H2O. This is hydrogen bonded to another water molecule. This is hydrogen bonded to another water molecule. Okay. Now what happens is that suppose here was 1 hour of our H2O. This H2O releases its proton and now this H2O becomes your OH minus. This H plus so released will move here and this will now convert itself into H3O plus. So this will become H3O plus. Now again this will release its proton, will become again H2O and this will become H3O plus. So this jumping mechanism from one hydrogen bonded water molecule to another hydrogen bonding water bonded molecule is actually what the proton is doing here, and that's why its overall conductance is very high and conductivity will also be very high. Why? Because conductivity is nothing but G multiplied by G star. OH minus is also conducting because it is acting as a partner in the relay race. It is passing this baton from one person to another and hence it is also contributing to the overall conductance and the conductivity. This is what we call as the Grothus effect. Now we have to talk about the conductometric titrations and the application of conductometric studies. So basically what happens in the conductometric titrations, whatever ion is present here, suppose this is our titrate and here I am taking titrant. Suppose here I had this A plus ions and here I had this B plus ions. So this B plus will replace this A plus. And when this will happen, when this replacing will be done, the overall conductance will be altered, the overall conductivity will also be altered, and this is what the conductometric studies are mainly focusing upon. Now we have to talk about the applications of conductometric studies. So the first important application is again to determine the degree of dissociation of the weak electrolyte. This can be done if we know the molar conductivity and the limiting molar conductivity. So we can easily calculate the degree of dissociation. One of the important applications and this application was also of the Kohlrausch law. The another important application is the determination of ionic product of water. Now we know that the ionic product is nothing but the concentration of H plus ions and the concentration of OH minus ions, and this ionic product is the value is 10 to the power minus 14. Now when we take ultra pure water, means there are no other impurities present, only H plus and OH minus are present. At that time the H plus concentration will be equal to OH minus concentration, and both of them will be 10 to the power minus 7 each. Means that time this H plus or OH minus concentration will be equal to simply the root of the ionic product, and this will be only applicable for ultra pure water, not in other cases. So here, for the pure water, the conductivity can be related to its molar concentration also. Now if we have to calculate the conductivity, how do we calculate it? We basically multiply the concentration of H plus by the limiting molar conductivity of H plus the concentration of OH minus multiplied by the limiting molar conductivity of the OH minus. So we are doing nothing but we are just multiplying the concentration of that ion with the limiting molar conductivity of that ion, so that we can get the overall conductivity. So this is what do we do. Now what happens after this? We can also write it as the conductivity is equals to the limiting molar conductivity of H plus, limiting molar conductivity of OH minus ions, and H plus and OH minus, the concentration is already equal to Kw, that is ionic product. So this is how we can derive the formula for the conductivity. Now if the ions are present in the low concentration, then the molar conductivities of H plus and OH minus ions taken together at infinite dilution, they will come out to be 547.6 Simon centimeter square per mole. See, what happens is when there is ultra pure water and the concentration of H plus and OH minus ions are equal but they are very diluted, so that time the limited molar conductivity of H plus and limiting molar conductivity of OH minus, it turns out to be 547.6 Simon centimeter square mole inverse. Okay, now after this we already know that kappa is nothing but it is equals to Kw, that is any product of water multiplied by H plus and OH minus, right? So this can also be written as Kw multiplied by 547.6, and Kw from here we can determine as kappa upon 547.6, and because it is ultra pure water it should be around 10 to the power minus 14. From there also we can determine the conductivity. Okay, it is sorry it is root of Kw, so here it comes out to be square. Yes, so this can also be happening. This formula can also be derived with the help of the conductometric titrations. So this is another application of conductometric titrations, that is to determine the ionic product of water. Third important application of these conductometric titration is to determine the solubility and the solubility product. Now one important formula which you should know is that molar conductivity is nothing but conductivity divided by concentration. We know this. Either we are multiplying by 1000 or even if we are not multiplying by 1000, that doesn't matter. But here we know this, that the molar conductivity is equals to the conductivity divided by the concentration, right? Okay. Alternatively, we can also write that the concentration is equals to the conductivity divided by the molar conductivity. And always remember that if we are calculating the conductivity of the whole solution, it is equals to that of the salt or the solute plus that of solvent, right? So if I want to calculate this for solute, it will be equal to the conductivity of solution minus the conductivity of solvent. And here this conductivity of salt divided by lambda m gives the concentration of that particular salt or particular solute. Now there is another important term what we call as solubility product. Now always remember that the concentration of the solute and the solubility of the solute is one and the same thing, but alternative forms of same. So the solubility product, which is also referred to as KSP, it is nothing but the solubility of that particular cation, or let's write solubility of that particular cation multiplied by the solubility of that particular ion, anion. So this is a solubility product, and you can just replace this C with S and you can get your solubility also. So solubility is nothing, solubility of a salt is equals to the conductivity of the salt upon the limiting molar conductivity. Through this also you can calculate the solubility. So this is third important application of conductometric titration. I know it's quite confusing, but if you just try to remember the formulas, you will be easily able to draw out the result. The fourth important is to calculate the hydrolysis constant. Now hydrolysis constant is Kh, and this is the fourth important application to calculate Kh. Simply you can remember the formula, it is C alpha square upon 1 minus alpha, and this hydrolysis constant or this K equilibrium are the same things then. So this is also what you need to know. Okay, one more important thing for the third application. We know that solubility is what? It is equals to the conductivity upon limiting molar conductivity, and solubility product is what? It is solubility multiplied by solubility. So this solubility product will be equal to conductivity upon limiting molar conductivity, it's a square. So this also you can add on. So these are the applications of the conductometric titrations. In our next video we shall study about the Hittov's method and the moving boundary method, and how do we calculate the transport number.